Welcome back to everyone. This is the second half of our lesson, which is the line of intersection, or commonly referred to as the LOI. Okay, we've touched on it briefly, and we've noted that when two planes intersect with one another, they form what we call as an LOI, or lines of intersection. Now, in engineering science 1, we have two cases wherein we have something that looks like this. This is what we call as case 1, when the planes seem to overlap. So clearly here, line 1, 2, 3, and ABC appear to be overlapping in both HRP and FRP view. While we have another case, which is case 2, and in this case, the planes do not seem to overlap. No? So we can clearly see that ABC is not overlapping with 1, 2, 3 for both HRP and FRP views. Now, you might probably be thinking, if the planes are not overlapping, then they should not have a line of intersection. But we take note that in mathematics, when we define planes, they are actually extensible surfaces, no? So they can extend up to infinity, and if two planes are not parallel to each other, then when we extend them to infinity, they will eventually meet at a line of intersection. And since the planes are extensible, then this line of intersection should also be extensible. In this video, I'll be showing case 1 first, when two planes seem to overlap. Then in another video, I'll show in more detail what case 2 is all about. So to begin, let's start with a visualization of case 1, where the two planes seem to overlap with each other. Okay, so let's take a look at these two planes, the blue triangle and the pink triangle. And we can observe in space, no, that one triangle appears to be piercing the other at a particular line of intersection. And in this case, it's the pink triangle piercing the blue triangle at this line of intersection. And we can actually clearly define that line of intersection, correct? This is the line of intersection. Now, one key observation is that the endpoints of that line of intersection is actually made of the two piercing points from the edges of the pink triangle. So if you look at the edge of this pink triangle right here, it actually pierces the blue triangle at this particular point. And this other edge of the pink triangle actually also pierces the blue triangle at this particular point. And when we connect those two endpoints, we actually form the line of intersection. Okay, so this makes us a lot of sense, no? Because if you think about it, planes are actually just a collection of lines, an infinite collection of lines at that. And when we look at the line of intersection, then we can actually think of it as just a infinite collection of piercing points. And to create a line, we just actually need two endpoints. Okay, and the endpoints here are the piercing points. Okay, so the next session now becomes, how do we know if a line or if an edge of a plane actually pierces the other plane? Because we could have something that looks like this, no? For example, if I move this pink triangle, then we can have something like this, where now this is a case wherein we still have a line of intersection, no? From this point to this point. So we have something like this. But now, in this particular case, the one edge of the blue triangle now actually pierces the pink plane right here. Okay, so it pierces it at this particular piercing point, and one edge of the pink triangle, this edge right here, pierces the blue triangle at this point. But still, if we connect those two piercing points, we can still create the line of intersection between the two planes right here. And we can try another orientation of something that looks like this. And now this is the other case wherein the two piercing points actually comes from the piercing points of two edges from your blue triangle piercing the pink triangle. So we have this edge right here, this edge. Oh, sorry. This edge right here pierces the pink triangle at this piercing point. And we have this other edge right here piercing the pink triangle at this particular piercing point. And in all of those cases, we form the line of intersection simply by connecting the two piercing points. Okay? So the question is, how will we know which edge of which triangle actually pierces the other triangle or the other plane? So the simple answer is we can't really tell right away, no? So that's why when we do case one, we actually need to test all of the edges if they contain a piercing point that is contained that pierces the other plane inside the plane itself. So in this particular case, we have to check all the edges of the blue triangle and check if they have a piercing point with the pink triangle. And similarly, we have to check all the edges of the pink triangle if they pierce the blue triangle. If you have two triangles like this, which contains three edges each, then you'll have to check all 6 lines if they have a piercing point with the other plane. The greater the number of edges that a plane possesses, the more lines you have to check for piercing points. It might seem overwhelming, but the good thing is you only need to find 2 piercing points, because for any given 2 planes that intersect with one another, there will only be exactly 2 piercing points that comes from the edges of each of the planes. Okay? So meaning, if for example in this case, in the first 2 lines you check, you luckily found the 2 piercing points, then you don't actually need to find the piercing points of the other 4 edges, no, because you can't find the piercing points inside the plane anymore. Okay, I hope that makes some sense, and let's try to apply this visualization in our actual engineering drawing. Okay, so we have this example where we are to determine the LOI of ABC and 1, 2, 3. The first step is to choose an arbitrary line and determine if it contains a piercing point or if it has a piercing point on the other plane. Okay, so let's try first line 1, 2. So we have line 1, 2 here, and we can use the cutting plane method now. So the cutting plane method works well here because, again, we don't have to create the auxiliary reference plane. Okay. So let's check 1, 2. So let's do the special cutting plane method. So this is 1, 2, the apparent intersection of 1, 2 and AC is at this point. So we project it down. And this is at line AC. So we put it at this particular point. Then we have the intersection of line 1, 2 with the line BC. And since this is line BC, we project it downwards until we find line BC located here. And then we connect these two, and this should give us the location of the first piercing point. So in our first line that we tested, we determined that line 1, 2 actually has a piercing point onto plane ABC located at this particular point. And then we can project the piercing point upwards to HRP. Now we can take another line, say line 1, 3, and let's do the cutting plane method again. So we take line 1, 3. This is the apparent intersection of line 1, 3 with line AC, and we project it downward. We should have this point. Then we have line 1, 3 with line BC, and project this apparent intersection downward up to this point, since this is the line BC. And then once we have this 2 points right here, we just connect them. And if they intersect with line 1, 3, then we can say through the cutting plane method that line 1, 3 has a piercing point onto plane ABC. So this is the piercing point. Then again, we can just project it upwards towards the HRP view so that we can find the piercing point in the HRP view. Okay. Now, once we have generated these 2 piercing points, what we'll actually do is just connect these 2 points, and the line that it creates, as we've alluded to earlier in the visualization part, is actually our line of intersection. Okay, so again, as I mentioned earlier, once you found 2 of the piercing points, you don't actually need to check the other lines if they have a piercing point. And luckily, in our example here, the first 2 lines that we chose, line 1, 2 and line 1, 3, do have piercing points onto plane ABC. But for example, if we chose 1, 3 and we determine that it does not have a piercing point, then we'll have to choose the other lines here. No? In this particular case, no, in the visualization part, I said that we need to check all 6 lines to determine if they have the piercing point. But in this particular case, we actually just only need to check 4 lines, no? Because if you notice, line AB does not overlap with plane 1, 2, 3, meaning it can never have a piercing point with line 1, 2, 3. Similarly, line 2, 3 here does not overlap with plane ABC, so therefore it is impossible for it to have a piercing point located inside the plane ABC. Once we have found this line of intersection, we now need to show correct visibility. So to show correct visibility, we need to check every line that is overlapping with the other corresponding plane. Okay, so let's first check line AC with line 1, 3. So this is its apparent intersection point. Let's project it downwards, and we can see that it touches line AC first, meaning that line AC is closer to the reference plane, and therefore it should be above line 1, 3. Okay, so this means that this will be now a solid line. So we can do that with every other apparent intersection, but we actually only just need this one solid line. No? So once we've determined that this is a solid line, we can determine the visibility of the other lines. This is a sort of shortcut. No? So anytime you encounter a apparent intersection point or a piercing point, then you will change visibility. So what do I mean by that? So let's just take this for example. So we have this apparent intersection point. So it's a solid line from here going to this point. And since this is apparent intersection point, we change visibility. So this becomes a hidden line. Hidden line up to this piercing point. So when it encounters a piercing point, it changes visibility. This becomes a solid line. So again, once it encounters a apparent intersection point, this now becomes a broken line. Again, it encounters an apparent intersection point, then therefore it changes to a solid line going towards here. And once it reaches this piercing point, it again changes visibility and becomes a broken line until we reach our initial point. No? So that's sort of just a shortcut that makes use of the alternate nature of your visible and hidden lines. But for some students, no, who have the innate ability to view planes in space in their mind, they can actually imagine the orientation of the planes, no, and by imagining what the orientation of the planes looks like in space, they can determine the visibility of each of the lines. So, for example, if I look at this plane AC, if this line AC right here, it's above your plane 1, 2, 3, right here. So therefore, everything that is in this region of the plane ABC should be above, and therefore this 2 lines here becomes broken lines. And since all of 1, 2 here is below AC, when it comes out from the line of intersection, then it should make some sense that it should be a solid plane. So this becomes a solid plane right here, and therefore, consequently, your plane ABC at this particular region will be below plane 1, 2, 3. So that's why this is a broken line. So a good tip I can give you is when you're trying to check for correct visibility in lines of intersection is that you just look at your final answer, no? Look at the final answer and try to imagine the planes in space. If the visibility you have drawn makes sense, because if you've drawn the wrong visibility, your final answer will look a little bit odd, no? And whenever you notice that your final answer looks a little bit odd, then try to check if your correct visibility is actually correct. Again, when we check correct visibility, all views are independent of each other. So meaning we have to check correct visibility for each of our views. Okay, so now that we've determined correct visibility in HRP, let's proceed with correct visibility in FRP. Here we check correct visibility between line 1, 3 and line BC. So we project this line upwards to FRP, and we see that the projection touches line BC before it touches line 1, 3. So this means that line BC is above, in this FRP view, line BC is above your line 1, 2, 3. So therefore, line BC becomes a solid line. And from here on, we can do the imagination technique, where we just look at the plane in space and try to imagine what it should look like and what makes the most sense. Or we can use the alternating technique, wherein each time we come across or each time we encounter an apparent intersection or a piercing point, we will change visibility. And if you're not confident with that, you can also individually check each of the lines or each of the apparent intersection points, and check correct visibility from here. So I can very well just, for example, this intersection point, I'll check line 1, 2 and line BC. So if I project it upwards, I can see that it touches line BC first. Therefore, line BC is above line 1, 2, and therefore this becomes a broken line. So I can also check it from this side. So I can see that I'll check if line 1, 3 is above line AB. So I project it upwards, and I'll see that it actually touches line 1, 3 first, as opposed to line AB, which is here. Therefore, 1, 3 is above, and so on and so forth. So I can check all of the lines. No, so you can do that if you're not confident with imagining it on your own, or if you find the alternating technique a bit confusing. No? But personally, I like to use a combination of the imagination, quote unquote, imagination technique and the alternate lines technique. This should be how the final answer looks like. So again, my tip, when you finish the plate, just look at it for a few seconds and try to see if it makes sense. No, if it looks odd to you, then probably there is something wrong. From here, let's try an exercise. We'll do part 2B of our module. This is part 2 of our module, and again, you can do this along with me. If you need more time, just slow down the video, or you can pause the video. Okay, so before we begin, let's try to do part 2A first. So the intersection of two planes, as we've discussed earlier, is actually a line, no? And which is also known as your LOI, or your line of intersection. Okay, so now let's go to part B. So we are to determine the LOI of the given line and plane. And I think this is a typo, no? Because a line and a plane does not give you an LOI, it gives you a piercing point. As we've discussed in the previous video, this is supposed to be the LOI of the given planes now, because only two planes, the intersection of two planes, can give you the line of intersection. Okay, and we are to show correct visibility. Now we are checking line AC onto plane 1, 2, 3. Therefore, the projection lines should be at or should be projected along the edges of the plane, no? So be very careful with this, guys, no, because this is the most common mistakes when it comes to LOI, no, when we're in because of the many lines involved, it gets confusing on where we actually project this particular point. And this line does not intersect with AC, and from what we've learned from the cutting plane method, is that if this line here, this is for reference, ito yung XY na ginawa natin last time. This line XY here does not intersect with line AC. Therefore, line AC does not pierce your plane 1, 2, 3. And when we check, it intersects our line 1, 2 at these piercing points. So we have found our first piercing point right here. And now let's proceed with the next line. So let's just do a circular pattern. No? So we started with AC, then we proceeded with 1, 2. So the next line is our line BC. Now let's check the last line, which is line 1 3 onto plane ABC. So I say last line because again we will not check anymore 2 3 and AB, since it is obvious that they do not overlap with the other plane. No? The line we created intersects with our line 1 3, which is line 1 3 here. So this is our piercing point. Now that we've found the LOI, we need to show the correct visibility. So I'll check the correct visibility for HRP first. We already have the projection lines, so this becomes infinitely easier. You would really benefit class from trying to look at or from trying to imagine the planes themselves, because it simplifies or it gives you a lot of confidence when you're actually drawing your final answer. Okay, so that's for your case 1. So in the next video we'll do case 2, wherein we are trying to find the LOI. Sometimes we call it as an imaginary LOI, of two planes that do not seem to overlap with one another. Okay, so I'll see you in the next video.